Sound 8, okay. Back to the meeting. Thank you. So should I start again? Thank you for giving me the opportunity to present the results of my work at this seminar. These results were obtained over the course of this year under the supervision of Dr. Peter Somberg. I'm happy he was able to join us today. So in this project, we were trying to compute characteristic classes of normal bundles of embeddings of Prague submanifolds, mainly using representation theory and Schubert calculus. So our overall goal is to understand the K-theory of the spaces, of the quotient spaces GP, where G is a complex semi-simple Lie group and P a parabolic subgroup of G. If we have such a, if you have a homogeneous space GP, then complex vector bundles over this space correspond to representations of the subgroup P. We are currently, we were analyzing the situation when we have another complex semi-simple Lie group G prime, which is also a subgroup of our big group G. And G prime has a parabolic subgroup P prime, which is equal to the intersection of the big parabolic subgroup P and the subgroup G prime. In this situation, we then have a natural embedding iota, which embeds the homogeneous space G prime quotient P prime inside G quotient P. And the embedding iota then induces a short exact sequence of vector bundles, or equivalently P prime representations. So in the middle, we can restrict the tangent bundle of GP over the subspace G prime quotient P prime. Inside this bundle, we can find the tangent bundle of G prime quotient P prime as a subbundle, and then we define the normal bundle of the embedding iota as the quotient bundle of the restricted tangent bundle and the small tangent bundle. We are interested in characteristic classes of the normal bundle and iota. We hope it could reveal some important or interesting information about the K-theory of the homogeneous spaces G prime, P prime, as well as GP, and maybe also about the induced map iota star in K-theory. And so far, we have been compute the characteristic classes of an iota when iota is embedding of complex Grassmannians. So maybe just to mention my notation, I denote GR and K, the Grassmannian of K-dimensional subspaces of Cn. So there are 3 sections to these presentations. In the first sections, I will recall some necessary knowledge about topology and cohomology of complex Grassmannians, complex in parentheses because real and quaternionic Grassmannians have very analogous topology and cohomology. As well as I will also recall some necessary representation theory of the special linear group, because complex Grassmannian is a homogeneous space of the special linear group SL and C. Then, in the second section, I will show the process or the constructions necessary to compute the Chern classes of the bundle and iota. And if time permits, I will hopefully be able to make some remarks about how we can compute the Chern classes of the tangent bundle of complex Grassmannian only from the knowledge of the Chern classes of the normal bundles. So the complex Grassmannian is a CW complex, and any K-dimensional subspace of Cn can be represented as a row space of a K times n matrix. You can denote it AB for now. and it can be the matrix AB of this form is actually unique. So this is an example for GR94. So this matrix, the row space of this matrix represents a four-dimensional subspace of C9. To a space V, we can assign strictly increasing sequence of indices T1 up to Tk, and these indices T1 denote which columns of the matrix which represents our space V are the canonical basis vectors of Ck. If we have two k-dimensional subspaces of Cn, we can divide them. We can sort them into equivalence classes based on whether they define the same strictly increasing sequence of integers T1 up to Tk for the matrix AB and AW. And we call these subsets the Schubert cells. The Schubert cells of complex Grassmannians correspond to partitions. So in the case of GR and K, its Schubert cells correspond to partitions of length K with maximum element less or equal to n minus K. So if we have a Schubert cell where all the subspaces in the Schubert cell define the strictly increasing sequence T1 up to Tk, we assign to it a partition lambda, whose if part is defined like this, and basically what it does, we just compute the number of the red zeros in each row. So this Schubert cell would correspond to partition 4, 2, 2, 1. Also, to a Schubert cell, we can assign the complementary partition, which is also a partition of length k with maximal element less or equal to n minus k, and it's basically the partition where it's basically formed by the star entries in this matrix. By the way, the star entries are independent arbitrary complex numbers. So the complementary partition for this Schubert cell would be 4, 3, 3, 1. So we count the number of stars in each row, but from bottom to top.
I ask this. So even you consider the unoriented a Grassmannian unoriented plane, right? A K plane.
Yes, of K planes. Mm-hmm.
So that's So that's the conclusion on the even notice there was the next slide. You say something about the conclusion. See, so even the consideration element.
Well, actually, in case of complex Grassmannians, there are no torsion elements in the homology and cohomology because actually the Schubert cell, which corresponds to partition lambda, has so if the Schubert cell C lambda corresponds to a partition lambda and the sum of lambda is L, then these Schubert cells corresponding to partitions lambda with sum equal to L form a free basis of the homology 2k times n minus k minus 2L. So it's even dimensional homology group. So there are no under this with this EW structure, the Grassmannian has no cells of ordered dimensions, hence all the homologies and cohomologies are free abelian groups.
Yes, so you consider complex.
Yes. Okay, so we've already mentioned how the partitions, respectively, the Schubert cells define free basis of the cohomology of the homologies, And if we denote by sigma lambda, the Poincare dual of the homology class of the Schubert cells lambda, then the class is sigma lambda with the sum of lambda being equal to L is a free basis of the 2L cohomology with integer coefficients of the complex Grassmannian. Just a little remark, the Poincare dual of C lambda, the element, the class sigma lambda, is equal to the Hom dual of the Schubert's of the class of the Schubert cell corresponding to the complementary partition. This remark is important because when we compute the associated maps, the induced maps in homology and cohomology, the cohomology maps are just the dualizations of the homology maps, and so it's convenient to work with the Hom dual basis. So it's good to have it related to the Poincare duals, because on the other hand, with the Poincare duals, we can then express the cohomology multiplication. Okay, so now just some recollection of the representation theory. So the complex Grassmannian admits a transitive action of the special linear group SLN. It's just induced by the canonical action of SLN on Cn. If we denote by E1 up to En the canonical basis of Cn, then the stabilizer of the k-dimensional subspace generated by the last k canonical vectors is the subgroup which we denote by P and K. It's a subgroup of SLN, and it consists of matrices of this form, where P1 is a regular invertible matrix, and by n minus k times n minus k. P2 is invertible matrix k times k, and the star entry is arbitrary k times n minus k matrix. And of course, the product of the determinants of the two diagonal blocks must be 1. So we can express the complex Grassmannian and K as the quotient space SLN over P and K. And then, so the inclusion of P and K into SLNC and then the quotient map into the Grassmannian is a principal bundle, and vector bundles over the Grassmannian are then associated vector bundles to this principal bundle, and they correspond to representations of the parabolic subgroup P and K. Yeah. So now, before we begin to describe the process of computation of the Chern classes of the normal bundles, so we need to consider the whole Grassmannian lattice. By lattice, I just mean this net of Grassmannians and their inclusions. So I will describe the maps alpha and beta right now. First, the vertical maps alpha and k, they include the Grassmannian of k-dimensional of k-planes in Cn inside Grassmannian of k-planes in Cn plus 1, and the map alpha and k is induced by the linear inclusion of Cn inside Cn plus 1 as the last n coordinates. It is induced by a Lie group homomorphism, which is on the level of SLN, is just defined by taking n by n matrix with determinant 1 and expanding it to n plus 1 times n plus 1 matrix with determinant 1. And on the level of Schubert cells, the map alpha and k maps a Schubert cell C of the Grassmannian nk to a Schubert cell of Grassmannian n plus 1k, and by this notation, I just mean that we take the matrix representing the subspaces of Grassmannian and K, and we just add a 1, 0 column at the end. So if I go back to this slide, so we would just add 1, 0 column to the right. It's the far. So the horizontal maps. Also maybe and on the level of partitions, we have a partition lambda 1 and lambda k, which defines the Schubert cell C. Then the image of the Schubert cell C defines a partition of still of length k, but now we can allow the first element to be less or equal to n plus 1 minus k. So we add plus 1 to each term of the original partition. And this corresponds to the fact that the partition is constructed by counting the number of zeros in the echelon form matrices. And if we add 1 0 column to the right, then we add 1 0 to each row. Okay, so now the horizontal map, eta nk includes the Grassmannian nk inside the Grassmannian n plus 1 k plus 1. So under these maps, even though the dimension of the subspaces increases, we preserve the difference n minus k. It will remain the same under this inclusion. And this inclusion of Grassmannians is induced by the canonical inclusion of Cn inside Cn plus 1, this time as the first n coordinates. And if we take a subspace B of Cn, we include it as the same subspace of Cn plus 1, and then we add to it the n plus 1, the new n plus 1 dimension we have now in Cn plus 1. As a Lie group homomorphism, it is induced by this inclusion of SL n into SL n plus 1. And on the level of Schubert cells, it maps a Schubert cell C to a Schubert cell where we add one row and one column to the matrix representing the Schubert cell. And at the level of partitions, the partition now so if the Schubert cell C is defined by this partition, then the partition defining the image can now have length k plus 1, but the first element still needs to be less or equal to n minus k. And so we add 1 a minus k as the first element, which actually corresponds to the fact that we now have n minus k zeros in the first row of the resulting matrix. This map, even though not specified in the Grassmannian lattice, it will be important for our computation. And it's the homeomorphism which identifies the Grassmannian nk with the complementary Grassmannians n minus k. And so we consider a non-degenerate symmetric bilinear form on Cn, which is defined by the anti-diagonal unit matrix. And we denote by like this the orthogonality with respect to the bilinear form defined by this matrix. And then we just define the map phi nk from gr nk to gr n a minus k by assigning to a k-dimensional subspace its n minus k-dimensional orthogonal complement. The map nk is also induced by an isomorphism of the group SLN, and it is defined by taking a matrix G, transposing it, inverting it, and conjugating it with S. It is the outer. So this GT minus GT inverse is actually the only non-trivial outer automorphism of SLN. And it's just conjugated by the matrix S. The map phi and k, well, the homomorphism of groups maps the parabolic subgroup P and K bijectively to Pn and minus K. And if we compose these two homeomorphisms, we get an identity. So like it's the map PNK is almost a involution. It's an involution on the Grassmannian where the K-planes have half the dimension of the total ambient space. In that case, it's an involution. The map PNK is cellular, and it actually maps any Schubert cell of GR and K to bijectively to a Schubert cell of G, R, and minus K, which can be easily checked just by computing the kernel of the matrix representing the given Schubert cell, finding finding the natural basis of the kernel, and then aligning it into a matrix. The map PNK induces a nice map in both homology and cohomology, and I have permuted in parentheses because the homology of GR and minus K does not need to have the same generators as the same homology of GR and K. So basically, the map PNK in homology and cohomology maps generators to generators, and in particular, this will be important for our computations. It maps the partition whose Young diagram is a column of length J to the partition whose Young diagram is the row of length J. So at the level of partitions or their Young diagrams, PNK acts by transposition of the Young diagrams. Okay, so for each J, we can to the Grassmannian lattice assign the associated. We can associate the cohomology lattice with integer coefficients. For brevity, we shall denote the 2J cohomology of GR and K as A, J, and K. And of course, these vertical maps are the maps alpha and K in cohomology, and the vertical maps are the eta and K in cohomology. So if we fix J greater or equal to 1, we can order the partitions of J lexicographically. Basically, we consider the ordering where we look at two partitions up to some index. Their parts are the same, and then there is the first index where the index E, where the eth part of one partition is greater than the eth part of the other, and we order the partitions according to this ordering, and it makes the column of length J is the first with respect to this ordering, and the row of length J is the last. So, and we denote by Rj the number of all partitions of J. The number of Rj is not really important, but it's just convenient to order the partitions like this. So these are the Poincare duals of the partitions, and they are also the generators of the J cohomology of 2J of Grassmannian to JJ. So there's a technical lemma about the cohomology lattice. So the J cohomology lattice stabilizes below and to the right from AJ to JJ, which basically means that if the dimension of the K-planes is greater than J, or and at the same time the dimension of the ambient space Cn is greater than 2J, then the 2J cohomologies are the same as the J cohomology of Grassmannian to JJ. So this is the example when J is equal to 3. In this case, there are only 3 partitions of the number 3. These are 1, 1, 1, 2, 1, 0, and 3, 0, 0. And we see that so this is like this is A363, and below and to the right all the H6, all the 6 cohomology groups are Z3, Z to the power of 3. So that's the first point of the lemma. The second point of the lemma says that if you look at the cohomologies of the Grassmannian 2jj, 2j minus 1j, 2j minus 1j minus 1, and 2j minus 2j minus 2, then the cohomologies look like this, and the maps in the induced maps are the obvious projections. So if we go up, we forget the last partition, and if we go to the right, we forget the first partition, and this basically is due to the fact that so the first point of the lemma follows from the fact that the Young diagrams of all the partitions of J fit inside J times J square.
I missed who proved its lemma.
Oh yeah, I proved this lemma in my constructions.
I see. Good.
Okay, thank you. So this slide is just like a sketch of the proof, and the argument is mostly about which partitions fit inside the J times J ambient square. So the fact that all partitions of J fit inside the J times J square, from this fact we can deduce that the cohomology lattice stabilizes from the position 2jj. The second statement of the lemma, this one follows from the fact that only that all the partitions of J except the column of length J and row of length J, they fit inside the J minus 1 times J minus 1 square. And the lemma also has a third point, and that's basically illustrated the best with this diagram. So if we take the Grassmannian 2jj and consider all the maps from G are J plus 1j, the composition of all of these maps into GR 2jj, then the induced projection, if we go up in cohomology, is just a projection on the partition which is the row of length J. I'm sorry, the column of length J. Conversely, if we consider all the inclusions of the projective space CPJ inside GR 2jj, then the composition in cohomology in the other direction induces projection of onto the partition which is whose M diagram is the row of length J. So we see that the composition that the kernel of this projection is the free subgroup generated by all the other partitions which are not the column of length J. Alpha star is the vertical projection, the horizontal projection onto the cohomology of CPJ. The kernel of this projection is the free subgroup generated by all the partitions which are not the row of length J. And conversely, the image of alpha star is stated the column of length J, and the image of eta star is the row of length J. And so we also have these short exact sequences of free Z modules. Again, we can illustrate it, the lemma, on the example J equal to 3. So this is the square from the second point of the lemma. this is the projection which omits the first z, and the projection from this z plus z onto this z is the omission of this first z. So the composition is the projection onto the third factor. And horizontally, so if we go from GR63 to CP3, then in cohomology we have the projection from here onto the first factor, which is this set. And yeah, and this square is just the square from the second point of the lemma. Okay. Yeah, this is the proof of the sketch of the proof of the lemma, and now we can move on to computing the Chern classes of the normal bundles to the embeddings alpha nk and eta nk. So here is just an axiomatic definition of the Chern classes, the definition I work with. So we define Chern classes as a unique sequence of functions which to a complex vector bundle assign classes CJE in the 2J cohomology with integer coefficients. Chern classes commute with pullbacks along continuous maps. We have the Whitney product formula for the total Chern class, which we denote by CE, and it's the 1 plus sum of all Chern classes. Chern classes vanish whenever J is greater than the rank of the complex rank of the vector bundle, and the first Chern class of the canonical line bundle over C to infinity has to be specified, and it needs to be a generator of the second cohomology. And so from now on, we choose it to be minus the partition, which is just given by the one box. It's the only partition of one. So it's minus the Poincare dual of this partition. Will be our choice from now on. So vector bundles over the complex Grassmannian GR and K. So recall that the subgroup, the parabolic subgroup P and K, such that SLN over P and K is the complex Grassmannian is of this form. We have the diagonal GL blocks and this arbitrary K times A minus K matrix. The tangent bundle to complex Grassmannian and K is defined by the representation rho and K on K times N minus K matrices, and I'm sorry, N minus K times K matrices, and this vector space is isomorphic to the quotient of the Lie algebras, where this P and K is the Lie algebra of this parabolic subgroup. And matrix-wise, the representation rho and K is defined like this. It takes the two diagonal blocks and conjugates the N minus K times K matrix B. And so it is induced by the adjoint representation of SLN restricted to P and K on this quotient. Now the normal bundles. So the embeddings alpha nk and eta nk induce these two short exact sequences. By alpha nk, we restrict the tangent bundle of grn plus 1 k. Then we inside it, we find the bundle, the tangent bundle of gr and k, and the quotient is the normal bundle of alpha and k. It is defined by the representation phi and k, and it is the contragradient representation of the standard representation of GLK on CK. And yeah, so this can be obtained by just analyzing the restriction of the representation of Pn plus 1 k if you restrict it to the inclusion of P and k inside SLN plus 1. And similarly, from the other short exact sequence, we obtain the normal bundle and eta and k, and it is defined by this representation C and k, and C is just the standard representation of the GL and minus k block on on Cn minus k. Maybe just for brevity, I will sometimes refer to the bundle n alpha n k as the vertical normal bundle because it is induced by the vertical maps in the cohomology lattice, and similarly n eta n k will be sometimes referred to as the horizontal normal bundle. This lemma, which I have also proved just by looking at how the representations of the parabolic subgroups restrict under these group homomorphisms. So the lemma is quite easy to prove, and it states many nice properties of the two normal bundles actually. So they behave very well with respect to pullbacks along the vertical and horizontal inclusions. Also recall that phi and k is the homeomorphism identifying gr n k and gr n minus k. So phi star and k pullbacks the horizontal normal bundles to the vertical normal bundles, and vice versa. It pulls back the vertical normal bundles to the horizontal normal bundles. Moreover, the tangent bundle of the Grassmannian is isomorphic to the tensor product of the two normal bundles, which is easy to see from the fact that the representation rho and k is basically the representation of P1 and the contragradient representation of P2 on the tensor product of Cn minus k tensor ck dual. Lastly, the last point of this lemma states that there is a short exact sequence, and by this D I mean the dual bundle or the dual representation. It is defined by the dual representation to the one defining the bundle and alpha and k. So it's just the multiplication by the P2 block of the parabolic subgroup. Okay. And now, so this is the main result of our project. The total Chern classes of the vertical and horizontal normal bundles. So we see that the Chern classes of the vertical normal bundle are, so the J Chern class is the partition, the Poincare dual of the partition, which corresponds to the column of length J, and dually the J Chern class of the horizontal normal bundle is the row of length J. So we can prove this theorem just by computing the Chern class of n alpha and k, and then if we use the previous lemma, which states that n alpha and k is just a pullback of n alpha and minus k under phi star and k, which we know that just permutes generators of the cohomologies. And we also know that it transposes some diagrams. So we can prove the point B from point A using the map C and K. So first we know that, so the proof is done by induction. And first we note that the normal bundles, the vertical normal bundles in the first column of the Grassmannian lattice, they are just normal bundles of embeddings of projective spaces. So they have complex rank 1, and they are dual to the restriction of the canonical line bundle over Cp infinity to just Cpn. So their first and only non-trivial Chern class is the Poincare dual of the partition of 1. And now we take k greater than 1 and assume that the statement holds for all holds for k minus 1 basically. So we assume that the Chern class of alpha n k minus 1 for all n is 1 plus the sum of the column partitions. And then we look at the pullback, at the horizontal pullback of the vertical normal bundle alpha 2 kk. It pulls back by the previous lemma to the normal bundle, to the vertical normal bundle over GR to k minus 1, and we also have this trivial bundle of rank 1, but that doesn't affect the Chern classes in any way. So now we can use inductive hypothesis to say that the Chern class of this pullback is again what we assume here, and this determines actually the Chern classes of n alpha 2 k k for all j less than k, and this is due to the fact that the J cohomology lattice by the previous lemma about the cohomology lattice stabilizes at a to aj jj and to the right and below from it. And so we know that for j less or equal to k minus 1, the cohomology lattice, when we do this pullback, is stable. So the Chern class is like the map eta star is the map eta 2 k minus 1 star is an isomorphism for the cohomologies 2, 4 up to 2k minus 2. So we have already determined the first k minus 1 Chern classes of n alpha 2 kk, and to compute the highest k Chern class of n alpha 2 kk, we observe that since this pullback is, so this bundle has rank k minus 1, complex rank k minus 1, so its kth Chern class must be 0, which means that the kth Chern class of of n alpha 2 kk must lie in the kernel of the horizontal inclusion eta 2 k minus 1 k minus 1. And from the previous lemma, we know that the kernel of this cohomology map is just the free subgroup generated by the column partition of length k. So then we take this map, which is just a projection onto the 2k cohomology of gr k plus 1k. And if we pull back alpha 2 kk, we get the normal bundle alpha 2k plus 1k. So now we are over the Grassmannian k plus 1k. And if we restrict the cohomology map onto the kernel of eta star k minus 1 k minus 1, we get an isomorphism onto the 2k cohomology of gr k plus 1k. Hence, it is enough to find the kth Chern class of this bundle. And this bundle, if we pull it back over CPK by the map phi k plus 1k, we get the normal bundle, the horizontal normal bundle n eta k plus 1, 1. So, and by the previous lemma, we have the short exact sequence, where here this is n alpha k plus 1, 1, and it's just the canonical line bundle over CPK. And from this short exact sequence, using the Whitney product formula, we can compute the Chern classes of this, because we know that this bundle, this is the trivial bundle of rank k plus 1. So it has trivial Chern classes. We know the Chern classes of this bundle. So from the Whitney product formula and the knowledge of the cohomology ring of CPK, we can compute that the total Chern class of n at k plus 1 must be so the K-Chern class of this bundle must be the row of length k. And then we have to pull everything back by the map p k plus 1 k star. We know that it just transposes this partition. So from this partition, we obtain so this is the row of k. We transpose it by phi star and obtain the column of length k. So we've computed the K-Chern class of this bundle. Then by the previous arguments, also the K-Chern class of n alpha 2 k k must be sigma 1 k. And previous lemma, together with the stability of cohomology lattices, determines that the K-Chern class of n alpha n k is sigma 1 k for all n, not just 2k and k plus 1. This concludes the proof of the point A of the theorem, and then, as mentioned before, the total Chern class of the horizontal normal bundle can just be computed by pulling the normal bundle back to the vertical normal bundle, whose Chern classes we now already know, and then we just use the fact that P star and K transposes the Young diagrams, and it takes these column partitions and makes them into the row partitions. And that concludes the proof of the theorem. So basically, in the cohomology lattice of Grassmannians, we've just now, now we know only the Chern classes of the normal bundle when we go just one step in the cohomology lattice, one step down or one step to the right. So we can also consider a more general embedding of Grassmannians, which is just the composition of the maps from maps alpha nk and eta nk. So these maps are commutative, so we can assume that we first go a few steps down in the lattice by the maps alpha, and then we go a few steps to the right by the maps eta. So we have again this short exact sequence of vector bundles over the Grassmannian GR and K, and we have the normal bundle and iota. And if we successively apply the properties of the normal bundles, if we go just one step in the lattice, then we obtain that the normal bundle of iota splits into direct sums of the normal bundles of the vertical normal bundle of the horizontal vector bundles, and we also have some trivial bundle left, but that's not important for the computations of characteristic classes. We see that the number of the vertical normal bundle is exactly so. This difference n prime minus k prime minus k is exactly the number of steps we needed to take down in the lattice, and the difference k prime minus k is exactly the number of steps we took in the direction to the right in the Grassmannian lattice when doing the embedding iota. So now just so this is Pieri formula. It is a rule how to multiply the Poincare duals of the partitions in the cohomology ring Grassmannian. In the case when one of the partitions is the row partition. So if we have the row partition of length L and mu is a general partition of length k and maximum element n minus k, so it defines a Schubert cell in GR and k, then the kappa product is the sum of the Poincare duals of those partitions, which can be obtained by adding L boxes to through the Young diagram of mu each box to a different column. And so this is like the standard form of the Pieri formula. And if we consider the map phi and k, which we know that transposes Young diagrams, so in particular it maps the Poincare duals of columns to Poincare duals of rows. We can use this map to also prove like a symmetric version of the Pieri formula, which states that if we have the column partition of length L and mu a general partition, then the cup product is the sum of those partitions that can be obtained by adding L boxes to the Young diagram of mu, and each box is added to a different row this time. We can use the Pieri formula to compute the Chern classes of the normal bundle and iota, because so first we can use the Whitney product formula. We know that C and iota, we know that n iota is just the direct sum of copies of n alpha n k and eta n k. So we can use Whitney product formula for the direct sum. And since the Chern classes of this bundle and this bundle are just the column partitions in this case and row partitions in this case, we can use the two versions of the Pieri formula to inductively compute this product, this cup product. So for example, when the index of the Chern classes is sufficiently low, the formulas are still pretty nice. So whenever k and n minus k are greater or equal to 2, we have that the only generator of the second cohomology squared is the sum of the two partitions of the number 2. In projective spaces, the square of this is just the row partition, and in the case of GR k plus 1k, the square of this generator is just this column partition. But anyway, the first Chern class is just the sum of the Chern classes of all these bundles, of the first Chern classes of the bundles appearing in the direct sum. And so if we add these exponents, we obtain n prime minus n times sigma 1. And the second Chern class, whenever k and n minus k is greater or equal to 2, is equal to this linear combination of partitions. This is not visible, but this is sigma 1 squared multiplied by this binomial coefficient. Okay, so now if there's 5 minutes. So okay, so I would like to make some quick remarks on how these computations can be used to also compute Chern classes of tangent bundles of complex Grassmannians. So first we need to consider the endomorphism bundle. For two vector bundles E and F over base space X, we define the home bundle as the dual of E tensor F. So in particular, we have the bundle of endomorphisms of bundle E, which is just the dual of E tensored with E itself. And in particular, we know that the tangent bundle is the home bundle of the dual of the normal bundle alpha nk into the normal bundle and eta nk. Then, after some manipulations with direct sums, we obtain that the direct sum of the endomorphisms of the dual bundle of the vertical normal bundle plus the tangent bundle is isomorphic to the direct sum of n copies of the vertical normal bundle. Using the splitting principle, the pullback of the vertical vector bundle over the variety of complete flags in Cn splits into k line bundles, and we can compute So the pullback of the endomorphism bundle splits into K trivial line bundles and these tensor products. Hence, we can compute also the Chern class or the pullback of the endomorphism bundle. We can see that. So if we use the product for the formula for tensor products of line bundles and Chern classes, this formula multiplies this formula. So these are some squares. Hence, we see that the odd Chern classes of the endomorphism bundle are trivial, and the even classes, even Chern classes are some polynomials in the Chern classes of the original bundle. So in this case, of the vertical bundle. So we can compute the Chern classes of the endomorphism bundle just from the Chern classes of the orbital bundle. And hence, from this splitting, so we have this direct sum, we know the Chern classes of this, we can compute them with Pieri formula. We know also the Chern classes of this endomorphism bundle, and then using with the product formula, we can also compute the Chern classes of the tangent bundle using this formula. This formula becomes particularly nice when K is equal to 2, so when we're considering Grassmannians of two planes, because in this case, the only non-zero Chern class of the endomorphism bundle is the second Chern class. That's because here, in this product, we sum over 1 less or equal to I less than j less or equal to 2. So here we only have 1 minus C1 L1 minus C1 L2, the whole thing squared. And so the jth Chern class of the tangent bundle is just the jth Chern class of the direct sum minus the j minus second class of the tangent bundle, which we can compute recursively, times the second Chern class of the endomorphism bundle of the boundary. That's the end of the presentation. I would like to thank you for your attention.
Thank you very much for very nice presentation, and the method is also very nice reason. Yeah. So could you comment on Martin Marken email yesterday, because he sent us.
Oh yes. So Martin Markel he wrote me an email in which he suggested that I may want to look at the work of Julius Korbaš, who, well, among his work is also like dealing with embeddings of flag varieties and computing. Yeah, and he was also, Julius Korbaš was also like interested in the induced maps by this embedding in cohomology, and maybe also like characteristic classes of vector bundles over such spaces. So I briefly looked at abstracts of some of the papers of Julius Korbaš, and I think his work may be related to what I've been able to do so far, and I think I might be able to maybe use his results in the future.
So what's the no intersection between what you presented today?
Well, I think it's like the two areas of math are very close and related, but I'm not sure if I didn't really look at his work in that much detail yet.
Yes.
So I'm not sure if.
But in extra, it would not figure. They didn't have abstract that time, right?
Oh yeah, I read the abstracts of some of the papers, and it seems like he was probably using similar tools to those that I'm using in my work.
The rest at the end, the result is different. I mean, they are to prove different thing.
Oh yeah, he proved the different things.
Yeah. Okay. So that is important. Yeah, thank you very much. So,
Can I ask a question? So maybe I missed part of the notation, but can you comment on what portion of all possible homogeneous vector bundles on Grassmannians do these Cohomology bundles cover? So do they occupy some special space in among all possible homogeneous vector bundles?
So we mean like if these normal bundles, if they so like how many vector bundles can be analyzed from using the knowledge of the normal bundles? Yeah. So far, like well, we know that the tangent bundle and the endomorphism bundle can be, well, many information about it can be deduced from the information about the normal bundles. I would like to try if we can maybe consider the exterior powers of the tangent bundle. So what the information about the exterior power can be maybe obtained from the information about the normal bundles we have so far. But I'm not really sure how large is the class of homogeneous bundles about which we could deduce some information from the normal bundles.
But is the entire class kind of known, like how to enumerate the different kinds of vector bundles?
Over Grassmannians or over Grassmannians? I'm not sure. I have to say.
Okay, well, maybe I don't know. And a follow-up question. So for a given one of these normal bundles, the Chern classes certainly provide some invariants, but are these invariants kind of sufficient to uniquely characterize those bundles, or are there like might be some other bundles that have all the same Chern invariants, but be topologically still within the homogeneous class?
Yeah, I'm not sure about that. Although it would seem that at least in the case of projective spaces where the K-theory ring is basically the same as the cohomology ring, so maybe there the normal bundles would be unique. Well, unique bundles with such first Chern class, maybe.
But K-theory is also in general not enough to characterize the topological type.
Yeah, that's true. I'm not sure how many to which extent the normal bundles are characterized by their Chern classes.
Okay,
maybe that remains to be seen.
Yeah, it would be interesting. Thank you.
okay, if there are no more questions, let us